All right, let's talk about a problem that has, I'm willing to bet, frustrated every single person who's ever written code. I'm going to show you a simple but really powerful technique to make those dreaded array index errors a thing of the past.
So let me ask you, what do you think it is? What's the single most common bug in all of programming? It's not some crazy complex algorithm or a sophisticated data structure. Nope, it's something way, way more basic. Yep, you got it. It's those off by one and out of bounds errors. Those tiny, infuriating little mistakes that have been a plague on developers since the very beginning.
And listen, these aren't just little annoyances. These errors are the secret culprits behind so many program crashes, wrong answers, and even some really serious security flaws. We're talking about small mistakes with potentially huge consequences.
But what if there was an elegant, almost foolproof way to think about arrays that could pretty much eliminate these bugs entirely? Well, there is. And it comes from, of all places, mathematics. It's called the half-open interval. So what in the world is a half-open interval? You'll see it written as square bracket A, comma B, with a square bracket on the left and a parentheses on the right. It just means a set of numbers that are greater than or equal to A, but, and this is the important part, strictly less than B. The key thing to remember is A is in, B is out. Okay, so how does this help us code? Well, think about any standard array. If it has a length of, say, n, what are its valid index positions? They're always 0, 1, 2, all the way up to and including n minus 1, right? And this is where it all clicks. The half-open interval from 0 to n, written as 0, n, is a perfect match for that range of valid indices. It includes 0 and goes right up to but doesn't include n. The array's length itself becomes this perfect, natural, exclusive upper bound. This, right here, is the whole game. And hey, don't just take my word for it. This isn't some new trick. The absolute legend, Ansgar Dijkstra, was arguing for this exact idea way back in 1982. He said starting arrays at 0 was better simply because of its mathematical elegance. He saw this clean connection decades ago. Okay, theory is great, but how do we actually use this start-end pattern in our day-to-day code? Specifically, how does it make our loops and array slices better? You know all those common mistakes? This one mental model just wipes them out. That constant confusion between using I less than n versus I less than or equal to n, gone. Messing up the translation from a one-indexed algorithm you read somewhere, much, much harder to do. Accidentally slicing off the last element of your array, not going to happen. This is about more than just being correct. It's about writing code that's way more intuitive. All right, time for the boss battle, binary search. This is one of those classic algorithms that is famous, or maybe infamous, for being incredibly easy to screw up with an off-by-one error. But we're about to tame it with one simple, unbreakable rule. And that rule, we're going to call it our loop invariant. Now, an invariant is just a fancy word for a condition that has to be true every single time our loop runs. For our binary search, it's super simple. The answer we're looking for is always somewhere inside our half-open interval, low, high. That's it. We never, ever break this rule. So let's trace one single iteration, step by sec. Our search space is the window low, high. We calculate the midpoint, mid. We check the value at that spot. Then we just shrink the window. If our target is in the right half, we set low to be mid plus 1. If it's in the left half, we simply set high to be mid. The key is, no matter what, the window gets smaller, and our answer is still guaranteed to be inside. And when you put the two approaches side by side, the difference is just night and day. The old way, with an inclusive range, it forces you into these while low equals high loops with finicky updates like high equals mid minus 1. It's a total minefield for bugs. But our half-open method? It's just a clean while low less than high with a simple high equals mid update. So many fewer edge cases to stress about. And here's the payoff. This is what it looks like when you put it all together in clean, beautiful Python. This lower underscore bound function finds the first spot a target could be inserted. And look at the setup. Low, high equals 0, len of seek. Right away, we've established our perfect 0 and interval. The loop is while low less than high. It's the exact logic we just talked about, and it is absolutely bulletproof. And you know the best part? All this clarity and correctness, it costs you nothing in performance.
The time complexity is still that super efficient O log n, which means it can chew through massive amounts of data in no time. And this version uses constant O of 1 space. It's the best of all worlds. Correct, clear, and blazing fast.
All right, that was a deep dive. So let's pull all this back and turn it into a super simple checklist you can start using like right now, every time you work with arrays. Here it is, number 1. From now on, you think in half-open intervals. Start, end. That's your new mantra. 2. For any tricky loop like binary search, just state your invariant. Remind yourself what must be true. 3. Be extra careful when you're converting algorithms that use one-based indexing. And 4, don't forget the edges. Always ask yourself, what happens with an empty array? So you've got the pattern now. You see how it works. Here's my challenge to you. Can you go back to some of your old code, look at it with these new eyes, and find one of those sneaky off-by-one errors? I have a feeling you can.